In the previous lecture, I mentioned that the change in length of an object is proportionate to the original length times the change in temperature. And so the proportionality constant is the temperature coefficient of thermal expansion, or the coefficient of linear thermal expansion. And let's do a couple of examples here. Let's say that we have two metal rods here, and each metal rod is the same length, 1.25 meters. Okay, and one is made of aluminum and one is copper. Both of them are at 20 degrees Celsius, and we heat them to 80 degrees Celsius. And so I want to know what is the difference in length between them. So here they are, some D, right here. And so I want to know what is the change in the length. Because right now the difference in length is 0 because they're both the same length. But if we heat them up, are they still going to both be the same length? Well, question, we need to know the coefficients here for copper and for aluminum. Okay, and so we just look that up. Okay, so for copper, it's 1.68 times 10 to the minus fifth inverse degrees Celsius. And for aluminum, it's 2.40 times 10 to the minus fifth inverse degrees Celsius. So that means the change in length of the aluminum rod, okay, is going to be equal to 2.40 times 10 to the minus fifth inverse degrees Celsius times 1.25 meters times the difference in temperature is 60 degrees Celsius. So the change in length of the aluminum rod is going to be equal to 1.80 times 10 to the minus 3 meters. The change in length of the copper rod is going to be 1.68 times 10 to the minus fifth inverse Celsius degrees times 1.25 meters times 60 degrees Celsius. So the change in length of the copper rod is going to be equal to 1.26 times 10 to the minus 3 meters. So in other words, the aluminum rod expanded more than the copper rod. So the delta D is going to be the change in length of one of them minus the change in length of the other one. And so the delta D comes out to be 0.54 millimeters. So even though they're the same length to begin with, when they change temperature, they're a half millimeter different. Now, that's not a huge difference there, but it does matter that different materials can be different. And so this is actually something that is useful. For example, you could have a bimetallic strip. So in other words, this strip is made up of two pieces of metal that are bonded together. And so what happens is, if you change the temperature, one tries to expand more than the other, and the only way that that works is for this thing to bend. Okay, and so this was for many, many years before the advent of digital thermostats. This was how thermostats worked, is that you had a bimetallic strip, and when it got hot, it would bend a little bit and break or either make electrical contact, or it would bend the other way if it got cool and break contact. And so you could actually turn on and off things with this bimetallic strip. This was in fact, it is still used in some applications where digital things don't work as well. For example, ovens, they don't work. The digital thermostats don't work as well at high temperatures, and you'll often still find bimetallic strips to cycle an oven on or off as the temperature changes. But this used to be how pretty much all thermostats worked.